Hello everyone and welcome back to your YouTube channel and welcome to this very simple, elemental, basic video of today. Today we are going back to the basic concepts, elemental concepts, and what we are trying to do is to provide an elemental understanding of one of the most important equations when you are studying power system operation, and that is the case of the power-angle relationship. Power-angle relationship has different applications. It can be used to define the maximum power transfer in a transmission line, but also when we are working with the classical method for rotor angle stability, the equal area criterion, we can use this power angle representation, this power angle relationship, to define the active power flow on the single machine infinity bus bar system. So today I have a very short video, very basic. And what I will do in this video, during this video, is to show you where this power angle equation, this power angle relationship is coming from. Because if you understand this equation, it will be easy for you to understand more complex concepts related with active power transfer, maximum power transfer in a transmission line, but also related with rotor angle stability. So without further delay, let me go into this video today. Let's start with a simple transmission line. You must remember that there are different ways to represent the transmission, the overhead transmission lines. We usually, for power system analysis, we usually use what we call the circuit models. Circuit models, we are using a representation that is a circuit that is mimicking the electrical behavior of the transmission line. They are different models, circuit model for the transmission line, and there are different ways to create those models. One of the most used criteria to classify those models is using the total length of the transmission line. Without going into very complex detail about the number, we can classify the transmission line models using the total length in short transmission lines, medium transmission lines, and long transmission lines. The model that we use for calculating the steady state electrical parameters and variables in those circuits, of course, they are extremely important because they define the total performance of the transmission line. The classification short, medium, and long transmission line is not relevant for this very specific video today. I know that there are very important concepts over there related with the rate frequency or nominal frequency used in the system, voltage levels, and so on. However, today, for simplicity, we will start this video using the most used and simplified model, and that is the short transmission line. In the short transmission line, what we are considering is just the effect of the series impedance that we can find in a steady state of a transmission line. And in this case, this series impedance is represented by a combination of resistance and inductive reactance. However, in many calculations, we can neglect the value of this resistance because typically in transmission system, the resistance is lower compared to the inductive reactance in the series impedance. And the reason is clear, because we create the transmission lines to transmit active power, so we want to minimize, reduce the active power dissipation in the cables in this series reactance. So today we are using this transmission line, the lossless transmission line circuit model that is presented over here. As you can see, we are having here just a very interesting model, where there is an inductive series reactance, and we have this very important voltage drop across them. So you must remember this circuit model is a single phase, that means line to neutral model, representing a classical three-phase transmission line. The terminal I represents the sending terminal, and the terminal K represents the receiving terminal. So what I am trying to tell you is that this circuit over here, represent basically the behavior of this very important transmission line, lossless transmission line, and this is the short model. If we want to calculate the electrical current in this circuit, well, basically we can use one of the most important law in the circuit analysis, and that is the Kirchhoff voltage law. Here in this equation, you can see that we are applying the Kirchhoff voltage law. So you can see that the sending voltage VI is equal to the voltage drop across the series inductive reactance, and in this case we use Ohm's law, J at multiplying the current plus the voltage at the receiving terminal, and that is the voltage Vk. We must remember this representation is using steady state AC steady state quantities. For that reason, we are using phasors. Now what I will show you is the phasor diagram. Here on the top right hand side, you can see that I include here a dotted line. This dotted line is defining the reference, and we are plotting in red color the current that is moving in the series impedance. And in this case, you can see that I assume that we are having a lagging power factor, so the phase angle phi-k, that is the angle between the receiving voltage and the current, is basically an angle that is defining a lagging power factor. That means representing a inductive load. So then we can use in this phasor diagram the voltage drop through the series reactance, and adding the phasors, you can use just basic trigonometric principles. You can obtain that this vector over here, this phasor that is in blue color, the larger one, is basically representing the sending voltage. So this is the classical phasor diagram that we will find when we are using the lossless transmission line model, and in this case is a short transmission line. So from this equation that we create using Kirchhoff voltage law, we can extract the current. So the current will be the sending voltage minus the receiving voltage divided by the series reactance, in this case the X. So equation number one is this same equation, but now I am using the impedance notation. And if we use the polar form representation, as you can see over here, the magnitude of the impedance is X, and the phase angle of this impedance is 90 degrees. So the next step is I want to write the equation defining the apparent power that is introduced in the sending terminal and that is the reason for the letter I. So in this case, remember, we are working and we are calculating is the apparent power, but this apparent power is coming from the sending terminal. So let me go here for a second, because in this slide you can see that we are using the subscript I, and that subscript is for the sending terminal. Okay, so it's simple to see that the sending power, apparent power, will be the phasor of the sending voltage multiplied by the conjugate of the phasor representing the series current. And this apparent power have a real part that is representing the active power in the sending terminal plus J multiplying the reactive power at that terminal. So from this equation, what I will do is just a very simple mathematic trick. Now what I will do is I will apply the complex conjugate in both sides of this equation. So on the left-hand side, I have the conjugate of the apparent power. On the left-hand side, I have P minus JQ. And here in the middle, now the conjugate of the current, complex conjugate of the current disappear. And now we have the complex of the phasor representing the sending voltage. So from there, what I will do now is just basically substitute the equation that we obtained in the previous slide, defining the current in this series reactance. And you can see that the definition is over here, Bi minus Bk divided by Jx. So now it's just question of using some mathematical properties. The first step is I will expand this product, and on the first term you can see that we are multiplying the conjugate of the sending voltage and the sending voltage. And on the second term, you can see here at the numerator, we have the sending voltage, the conjugate of the sending voltage multiplied by the receiving voltage. Next step, I continue expanding the equation, but now I am using polar representation for every single of the phasors and impedances. So the denominator changed from Jx to X with a 90 degree. And the numerator, I have done the same. In the previous page, I defined the phase angle for the sending voltage and the receiving voltage. So now it's question to apply the properties of multiplying complex numbers using the polar representation. And in this case, we have the square value of the magnitude of the phasor of the sending voltage divided by the reactance. And this angle will be negative because we are having the conjugate. Here we have the same angle, so this minus this is 0, and this 90 degree is moved to the numerator as minus 90. So we are doing the same here, again applying properties of complex numbers in polar representation, and we arrive to this beautiful equation over here on the right bottom. You can see that this is basically the complex power or the apparent power, and these two terms on the right hand side, they are complex quantities. So now the next step, my viewers, the next step is I am interested on the active power Pi. So what I need to do is taking the real part of this complex equation number 3. So you must remember that if we are using polar representation, polar form representation, we can use this very important complex property, and that means that the polar representation can be transformed in rectangular representation by using the magnitude of the complex number and using the sine and cosine of the angle. So after applying this very simple mathematical or complex property, we obtain that the first term will be the square the square value of the magnitude on the sending terminal voltage divided by the reactance, the cosine of minus 90, and on the right hand side we have here this second term. Now let me analyze something quite simple. The cosine of minus 90 is equal to 0, so the first term here on the right hand side of this equation disappears because we are multiplying by 0. So the equation number 4 is here and is only representing the remaining term of this equation. So as you can see, the equation is minus Vk multiplied by Vi divided by x, cosine of minus delta and minus 90 degree. The next step is I would like to simplify this cosine, and what I will do is use a very simple trigonometric property, and we know that the cosine of the sum of two angles is equal to the cosine of the first multiplied by the cosine of the second minus the product sine A sine B. So now applying this property that is here in black color to the equation number 4, well, you will realize that inside this square bracket you can see cosine of delta multiplied by cosine of 90. But this cosine of 90, of course, is 0, and the sine of 90 here on the left-hand side term is 1. So finally, you will see this equation that you can find in many, many books related to power systems, and that is Vk multiplied Vi divided by x sine of delta. So equation number 5 is extremely important because equation number 5 is defining the active power that you can't transfer using a short transmission line, a lossless transmission line, and you are defining this active power transfer using the very important series inductive reactance, the magnitude of the terminal voltage, and you must remember this angle delta is basically the phase angle between the sending voltage and the receiving voltage. So in order to show you how important is this equation, right now what I will do is we want to use this equation number 5. We want to plot this equation number 5, and that is what we call the power, the P delta or power angle representation. Basically, you can see over here the vertical axis, this axis over here, y-axis, is representing the active power, and on the horizontal axis, you are representing the phase angle delta. And remember, this delta is the angle between the sending and receiving voltage phasors. So if this angle is increasing, you can see how the active power is increasing until reaching the maximum value. And if the angle is still increasing after that, well, the situation is now that the active power is reduced. So this equation number 5, assuming terminal voltage constant and the series reactance constant, has a very interesting behavior with this sign of the angle delta. And this is a trigonometric function that is creating this beautiful representation. One important conclusion over here is that 90 degree is the angle that defines the maximum transfer in this lossless series transmission line using the short line model. So this angle over here, 90 degree, is representing the maximum power. And as you can see over here on the right top, this maximum power represents the relationship between the magnitude of the terminal voltage, and here in the denominator you can see that we have the series inductive reactance. Conclusion very important over here is that to control the active power in a transmission line, well, we can use the angle delta. However, modifying the angle delta is very complicated and difficult when we are working in multi-machine, highly interconnected transmission systems. And if we look over here to the equation defining the maximum transfer, you can see that the numerator is basically the product of the magnitude of those phasor voltages, sending voltage and receiving voltage. And something that is very important is that controlling voltage is something that can be done by several mechanisms. However, you must remember that because security, operational security, the magnitude of the voltage, they cannot change so much. In typical transmission lines, of course, depending on the standard, depending on the country, depending on many factors, we have what we call the voltage regulation. In some transmission systems, that voltage regulation can be 10%, or in other countries 5%, and in few cases can be 2% or even less. So as you can see from the maximum power transfer, you can see that that number in the numerator is not so flexible because we have only 2% or 1% or up to 10% to modify the voltage. So to define a higher maximum power transfer, what we can do is affecting the denominator of that equation. In other words, what I am telling you is, in order to modify the maximum power capability, what we can do is modifying the series inductive reactance. That modification is beyond the scope of this video, but is related with some additional components that we use in the electrical power system and we call FACS. However, in order to conclude this very amazing video, again, what I want to remind you is that this equation over here, the equation number 5, is basically defining the relationship between active power and the angle delta. Those voltages are in a steady state AC quantities and represented by phasors. So this purple line here in the power angle representation define a steady operating positions that they are possible using the transmission line. So we are reaching the end of this video, and the idea of this video was to introduce some elemental concepts and create a basic understanding about the power-angle relationship. And in this case, I started with the most simple case that you can think about, and we are talking about the lossless short transmission line that is represented only by the series inductive reactance. So in the next video, I will start to discuss one of the very important aspects, because in reality, transmission lines, there are some losses. So it's very important for all people to understand the effect that those losses are creating on the performance, the steady-state performance of the transmission lines. So in the next video, I will keep working with those elemental understandings, power-angle relationship, but now I will like to show you how the equations change when we are using or considering the active power losses. So this is all for this video today. Thank you so much for watching, and I will see you at the next one. Bye now.